Welcome back to the deep dive.
And today we are really jumping into the deep end.
We really are. We've got a set of pretty technical lecture slides in front of us, all about statistical physics, thermodynamics.
It's a topic that, it governs almost everything, but it's usually hidden behind some really dense mathematics.
Right. And our mission today is to strip away that jargon, get past the noise, and really deliver the core knowledge you need. We're trying to do something pretty ambitious here.
We're moving beyond the basics, beyond things like simple pressure or even the velocity distributions we've looked at before.
Okay, let's unpack this. We're zooming way out. The goal today is to decode the fundamental rules for how energy spreads out in any system.
From the tiniest quantum particles all the way up to the atmosphere of the planet.
And to do that, we have to get our heads around one single equation, the Boltzmann distribution. The sources call it the master key to understanding why the universe works the way it does.
That's not an exaggeration. We're shifting from asking how fast are things moving to a much bigger question. How do particles arrange themselves across all the possible energy states they could ever occupy?
So to start this deep dive, let's set up the thought experiment that the sources kick off with.
Okay, so imagine the molecules in a system. Let's just say a gas in a box. Not just as little balls bouncing around, but as tiny oscillators.
And because we're at that microscopic scale, we have to bring in quantum mechanics right away.
We have to. And the first rule of quantum mechanics here is that energy isn't continuous.
It's not a ramp, it's a staircase.
Exactly. It's quantized. You have these very specific, discrete energy levels. We can call them E1, E2, E3, and so on.
And for this model, the gap between each step on the staircase, this delta E, is constant.
That's the simplification, yes. And on each of these steps, you'll find a certain number of molecules. So you have N1 molecules on level E1, N2 on E2, and so on. We call those the occupation numbers.
But this system is never still, right? It's a constant chaos of activity.
It's a riot of activity. Molecules are always colliding, swapping energy, jumping up and down that staircase. But, and this is the key, the total energy of the system stays the same. And the total number of particles, N, stays the same.
And that constant balanced chaos is what we call thermal equilibrium.
Precisely. The slides give a great example of what one of these little energy swaps looks like. A collision might knock a molecule from energy level 3 down to level 2.
But that energy has to go somewhere to be conserved.
So at the same time, another molecule has to gain that exact amount of energy, maybe by jumping from level 5 up to level 6. This constant, balanced exchange is the very heartbeat of a system in equilibrium.
So with all this shuffling going on, the big question becomes, what's the most likely arrangement? What set of these occupation numbers is the most stable, the one the system will always return to?
And that's really all thermal equilibrium is. It's just a physicist's term for the state of maximum probability.
To find that, we have to dive into the math of chance, combinatorics.
It's like the ultimate molecular lottery, If you have N total molecules, you have to calculate W, that's statistical weight. That's the total number of ways you can arrange those N molecules on all those energy levels.
And that's where we hit the first real wall of complexity.
We do, because the formula for W involves these massive factorials. It's N factorial, divided by the product of all the occupation number factorials. N1 factorial, N2 factorial, and so on.
And we're talking about n being something like 10 to the 23. You can't calculate the factorial of a number that big.
You can't even write it down. It's computationally impossible. And this is where the genius of the whole approach comes in.
Okay, hold on. You can't just skip that. If the numbers are that big, how do you work with them at all? What's the mathematical shortcut here?
That is a fantastic point. The trick is to stop trying to work with W directly and instead work with something else. Entropy.
Ah, okay. The famous equation, S equals KB log W.
Exactly. S is the entropy, and Kb is the Boltzmann constant. That equation connects the statistical world of W to the physical, measurable world of entropy, S. And the state of maximum probability, equilibrium, is also the state of maximum entropy.
So instead of trying to find the maximum of this impossibly huge number W, we just find the maximum of its natural logarithm, log W.
And that solves two problems at once. First, the logarithm turns those giant products into manageable sums. And second, for numbers this big, we can use a tool called Stirling's approximation to simplify the log of a factorial.
It turns a multiplication nightmare into a calculus problem.
A simple differentiation problem, yes. So we're just looking for the point where the probability curve is flat at the top, the point where a tiny change doesn't increase W anymore.
Which brings us back to that little energy swap we talked about. A molecule goes from E3 to E2, and another goes from E5 to E6.
We don't need the absolute probability. We just need to look at the ratio of the new probability to the old one, P new over P old, or W new over W old.
And I'm guessing a lot of things cancel out.
Almost everything. When you write out that ratio of the factorials, since only 4 of the occupation numbers have changed, all the other terms, millions of them just cancel. The ratio simplifies down to something incredibly simple.
What is it?
It's approximately the product of N3 and N5 divided by the product of N2 and N6.
That's the algebraic heart of the whole thing, and this is where the insight about equilibrium comes in. If the system is already at its most probable state,
Then that tiny little energy swap shouldn't change the probability at all. W new must equal W old.
which means their ratio has to be 1.
It has to be 1. So that simple fraction we found, it must be equal to 1.
If you rearrange that, you get something profound. You get N3 divided by N2 equals N6 divided by M5.
And that's the eureka moment. It tells us that the ratio of occupation numbers of any two adjacent energy levels, like Ni plus 1 over Ni, has to be a constant, all the way up the ladder.
So if the population drops by, say, 90% from level 1 to level 2,
Then it has to drop by exactly 90% from level 100 to level 101, even if there's hardly any molecules up there to begin with.
okay, so that's the rule. Now, the mathematical question. What function has that property where it changes by the same factor for every equal step you take?
That is the very definition of the exponential function.
So the occupation number, n, must be proportional to E raised to some constant times the energy level index.
Exactly. And since the energy E is just proportional to that index I, we can say the number of particles at a given energy, n of E, is proportional to E raised to some constant, let's call it beta, times E.
We have the shape of the function now, e to the beta e. But we need to know what that constant beta actually is in the real world.
Right, and this is where you link it back to the formal thermodynamic definition of entropy and temperature. When you do the full derivation, which we won't do here.
We'll spare everyone that.
Yes, but when you do, that mysterious beta is revealed.
And what is it?
It turns out to be -1 over kBt. The Boltzmann constant, Kb, is just there to convert energy units to temperature units. The T is temperature, and the negative sign is critical,
Because it means the number of particles goes down exponentially as the energy goes up.
which is exactly what we observe. And there you have it, the Boltzmann distribution. The number of particles at an energy E is proportional to E to the minus E over kBt.
One formula to describe how energy is shared across the entire universe at equilibrium.
The implications are just. They're everywhere. It explains why a hot object cools down. The energy is seeking its most probable, widespread, low-energy state. It explains why chemical reactions need a little push of activation energy to get started.
And temperature T is the master control. A high temperature makes that denominator, kBt, really big.
But it makes the exponential flatter. More particles have enough energy to reach the higher states. The energy gets distributed more evenly.
But as you cool the system down toward absolute zero, T gets tiny.
And that exponent becomes a huge negative number. It forces almost every single particle down into the lowest possible energy state. It's the blueprint for everything.
So that derivation gives us the rules of the game. Boltzmann tells us how particles are spread out, but now we need to look at the system's total budget. How much energy can it actually store?
And that brings us to heat capacity. But to understand that, we first need a really solid grasp on the idea of a degree of freedom, which we call F.
Okay, so what exactly is a degree of freedom?
It's any independent quadratic way a particle can store energy.
The word quadratic sounds important there.
It's the key. It means the energy term has to involve something squared, like velocity squared for kinetic energy, 1/2 mv squared, or position squared for the potential energy in a spring, 1/2 kx squared.
So these are like the different slots or pockets that a particle has for holding on to energy?
That's a great way to put it. And once you know how many slots there are, you can use one of the most powerful rules in all of classical physics,
Yeah.
the equipartition theorem.
Well, what does that say?
It says that in thermal equilibrium, the universe is incredibly fair. It divides up the available thermal energy democratically. Every single one of those quadratic degrees of freedom gets, on average, the exact same amount of energy.
And how much is that?
Exactly 1/2 kBt.
Okay, so let's start counting these slots. We'll begin with the simplest case, a monoatomic gas, something like helium or argon.
A single atom is basically a point in space. It can't really rotate in a meaningful way, and it can't vibrate.
Yeah.
All it can do is move.
So it can move in the x direction, the y direction, and the z direction.
3 independent directions. That's 3 translational degrees of freedom, so F equals 3.
Which means, according to the theorem, the average energy of a single helium atom is 3 times 1/2 kBt, 3/2 kBt.
Simple, clean, and a perfect match with experimental data.
But the real test comes with more complicated molecules, right? Things that can do more than just fly around.
Exactly. Let's move on to diatomic gases. Say
Mhm.
oxygen, O2, or nitrogen, N2, the air we're breathing.
We can model this as 2 balls connected by a stiff rod, the dumbbell model.
Right. So first, let's count translation. The whole dumbbell, its center of mass, can still move in X, Y, and Z.
So that's still 3 degrees of freedom, no change there.
No change there.
Mm.
But now, rotation. A three-dimensional object like a dumbbell should be able to rotate around 3 perpendicular axes, right?
That would be my guess. But the sources are very clear that it's only 2. Why is 1 missing?
And this is the first time quantum mechanics crashes the classical party, even at room temperature.
Ah, okay. What's the issue?
Imagine the 2 atoms are connected along the x-axis. Now think about rotating it around that x-axis like spinning a needle on its point.
The mass is all concentrated right on the axis itself.
So the moment of inertia for that specific rotation is incredibly tiny. It's almost 0.
And what does a tiny moment of inertia mean for the energy?
It goes back to our quantum staircase. A tiny moment of inertia results in huge energy gaps between the rotational quantum levels. The first step on that specific ladder is a mile high.
So even though the molecules are constantly bumping into each other, they just don't have enough energy to make that first jump.
The average thermal energy, kBt, at room temperature is nowhere near enough. So that degree of freedom is effectively inaccessible. It's frozen out.
So we don't count it. That leaves us with rotation around the other 2 axes, the ones that are perpendicular to the bond.
And that gives us 2 rotational degrees of freedom.
Okay, what about the third option? Vibration. The 2 atoms pulling apart and squeezing together like they're on a spring.
Vibration's an interesting one. A single mode of vibration actually counts as 2 degrees of freedom
Why 2?
because it involves 2 kinds of quadratic energy storage. You have the kinetic energy of the atoms moving, and you have the potential energy stored in the bond as it stretches and compresses.
So if it were active, one vibration mode would add a full kBt to the particle's energy budget.
It would. But for most diatomic gases like nitrogen and oxygen at room temperature, those bonds are very stiff,
Ah, and stiff springs mean high vibrational frequencies.
which means huge quantum energy gaps. Just like with the frozen rotation, room temperature just isn't hot enough to get those vibrations going, so they are freezing out too.
So for the air around us, the final count is 3 for translation, 2 for rotation, and 0 for vibration,
A total of F equals 5.
which means the average energy per air molecule is 5/2 kBt. And that prediction, coming straight from this counting method, is the key to understanding the heat capacity of air.
It's the foundation for it, absolutely.
We figured out the energy per particle, so now let's scale that up to the real world with heat capacity. C.
This is really the substance's thermal inertia. If you put a certain amount of energy in, how much does its temperature go up?
The theory seems pretty direct. The total energy in a system is the number of particles, N, times the energy per particle, which is F over 2 kBt. So C should be proportional to N times F over 2 times kB.
Right, but the heat capacity for, a bucket of water is different from a swimming pool. To compare different substances, we need to standardize it.
And that's why we have specific heat capacity, little c. It's usually measured per unit of mass. That's the number you see on food labels, like the 4,180 joules per kilogram Kelvin for water.
But for what we're doing, for fundamental physics, there's a much more elegant way to do it. We use the molar heat capacity, C mol.
We measure the heat capacity for exactly 1 mole of the substance.
1 mole being Avogadro's number of particles, Na.
Yeah.
By doing this, we're comparing atom for atom or molecule for molecule. The chemical identity almost fades away, and all that matters is the structure, the F value.
And this is where the math gets really beautiful. We take our formula for C, and we just replace the particle count N with Avogadro's number, Na.
So C mol becomes F divided by 2 times the product of Na and Kb.
And that product, Avogadro's number, times Boltzmann's constant, is another famous number.
It's the universal gas constant, or about 8.31.
So the prediction from all this statistical theory boils down to this incredibly simple rule. The molar heat capacity is just F divided by 2 times R.
That's it. You can count the degrees of freedom, you can predict the heat capacity. And this is where the theory gets tested against reality.
So let's run the numbers. For our monoatomic gases like helium, F is 3. The prediction is 3/2 R. That's roughly 12.5 joules per mole Kelvin.
And the experimental value for helium is 12.6. For argon, it's 12.4.
It's a perfect match, a direct confirmation that they only have those 3 translational slots.
Exactly.
Okay, next up, diatomic gases at room temperature. We decided F equals 5, 3 translation, 2 rotation.
The prediction there is 5/2 R, which is about 20.8 J per mole Kelvin.
And the measurements?
Oxygen is 21.0. Nitrogen is 20.8. Again, rock solid. It not only proves the equipartition theorem, but also confirms our quantum reasoning for why one of the rotations is frozen.
No, for solids. The atoms are locked in a crystal lattice. They can't move around, so translation is 0. All they can do is vibrate.
Right. They can vibrate around their fixed positions. And as we said, one vibration has 2 degrees of freedom. One for kinetic energy, one for potential.
And they can do this in 3 dimensions, X, Y, and Z.
So that's 3 directions times 2 forms of energy storage. That gives us a total of F equals 6 degrees of freedom for every atom in a solid.
So our prediction for the molar heat capacity of a solid is 6/2 R, or simply 3R.
3R. That works out to about 24.9 joules per mole Kelvin. And this famous result is known as the rule of Dulong and Petit.
The history there is amazing. They came up with this rule experimentally back in 1819. They had no idea why it worked. They just noticed that for most solid elements, the heat capacity was about the same.
It took nearly 100 years for statistical mechanics to explain why 3R was the magic number.
And if we look at the data for common metals, iron, lead, silver, they all hover right around that 24.9 value at room temperature.
It was seen as a universal law for solids.
But as the source material points out, there was one glaring massive exception that broke the whole classical model: diamond.
Right. While iron is right there at 24.9, diamond comes in at a tiny 5.9 joules per mole Kelvin.
The theory just completely fails. So what is going on with diamond?
The problem isn't the theory itself. It's our assumption that all 6 of those degrees of freedom are actually active and available for storing energy.
So this is where we need to resolve the diamond mystery. We know the 6 vibrational degrees of freedom should be there, but the measurement suggests only 1 or 2 of them are working.
It means the rest are frozen out, even at room temperature.
And we have to go back to our quantum rule for that.
Exactly. A degree of freedom only participates if the energy gap between its quantum levels, delta E, is smaller than the available thermal energy, kBT. If the gap is much bigger, the slot is locked.
And for vibrations, that energy gap is determined by the frequency of the vibration. Planck's relation, E equals h nu.
That's the link. Diamond is the hardest material we know. The carbon atoms are locked together with incredibly strong bonds.
In our spring analogy, these aren't soft, floppy springs. They are extremely stiff.
And very stiff springs vibrate at extremely high frequencies.
So high frequency means a huge energy gap between the vibrational states.
Huge. And at room temperature, around 300 Kelvin, the little packet of thermal energy, kEBT, is just not big enough to excite those vibrations. It can't make the jump.
So those 6 degrees of freedom are there in principle, but they're just inaccessible. They're frozen solid. And that's why diamond has such a low heat capacity. The energy you put in has almost nowhere to go.
And this reveals that heat capacity is profoundly dependent on temperature, something the old classical Dulong-Petit rule completely misses.
So what happens if you really change the temperature?
Well, look at the graph for a normal metal, like lead. At room temperature, it's right on the 3R line. Its bonds are softer, so all 6 modes are active.
But if you cool it down...
As you cool toward absolute 0, P drops, so kBT shrinks. Eventually, kBT becomes too small to excite even lead's softest vibrations. The modes start freezing out, and the heat capacity just plummets towards 0.
So statistics gives us the general rule, the equipartition theorem, but quantum mechanics sets the boundaries for when that rule actually applies.
It's the perfect combination. And you can see the reverse with diamond. If you heat it up, way up, past 1,000 degrees Celsius, kBT becomes big enough to start exciting those stiff vibrations.
And its heat capacity starts to climb up towards the classical 3R value.
It does. It proves the degrees of freedom were always there. They were just locked away at lower temperatures.
It's an amazing synthesis of the 2 biggest ideas in modern physics.
It really is.
We've been throwing around a lot of these measured values, 12.5 for helium, 20.8 for nitrogen, the 5.9 for diamond. I think it's important to take a moment and understand how physicists actually get this data.
That's a great point. The theory is elegant,
Yeah.
but it's all built on the foundation of incredibly precise measurement. The instrument is the calorimeter.
The sources outline two main types. Let's start with the modern high-precision one, the Nernst or electrical calorimeter.
This is what you use for serious research, especially for those low-temperature curves we were just talking about. The whole philosophy is about isolation.
You take your sample and you put it in a vacuum chamber.
Right, to eliminate any heat transfer to the outside world through conduction or convection, you want to make absolutely sure that every bit of energy you add goes into the sample and nowhere else.
And you add that energy electrically.
With a small heating coil, you pass a known current, I, at a known voltage, U for a precise amount of time, delta T. So you know the exact energy input, E, is just U times I times delta T.
And then you measure how much the temperature rises, delta T. The heat capacity, C, is just the energy you put in divided by the temperature change.
It's a very clean, direct measurement. And it's that level of precision that allowed physicists to see heat capacities dropping to zero, which was the evidence that demanded a quantum explanation.
Okay, now for the classic method, the one you might do in a school lab, the mixing calorimeter.
This one is less about ultimate precision and more about a direct application of the law of conservation of energy.
You take a hot object, you drop it in cold water, and you see what the final temperature is.
Simple as that. The energy lost by the hot object must equal the energy gained by the cold water. But there's a small catch.
The container itself, the cup or vessel you're using, also heats up.
It does, and you have to account for that. The way it's done is by defining the water value of the calorimeter.
What's that?
Instead of dealing with the heat capacity of the brass or plastic of the container, you figure out how much water would have the same heat capacity as the container.
So you just pretend your container has a little bit of extra water in the calculation.
Exactly. So the energy balance becomes energy lost by the sample equals the energy gained by the actual water, plus the energy gained by the water value of the container. And from that, you can solve for the unknown heat capacity of your sample.
So these two methods, from the high-tech Nernst to the classic mixing experiment, are how we get the hard data that either confirms or challenges the statistical theories.
They're the bedrock of the whole field.
Okay, we've seen Boltzmann's law work for tiny quantum states inside a single molecule. For our last section, let's see how this same rule applies to something enormous, the entire atmosphere of the Earth.
This is the perfect way to finish, because it shows the absolute universality of the principle. We're going from the microscopic to the macroscopic.
Now, if we were talking about water in the ocean, the pressure is simple. It just increases linearly with depth, because water is basically incompressible. Its density is constant.
But air is not incompressible. Not at all. The weight of all the air above us compresses the air at sea level, making it much denser. As you go up, there's less weight above you, so the pressure and the density both drop off.
So we can't use a simple linear formula. We have to think about it differentially. We have to look at how the pressure, dP, changes over a tiny little slice of height, dH.
And that change in pressure is just due to the weight of that little slice of air. So dP is equal to minus the density, rho times gravity, g times the height of the slice, dH.
The minus sign is because pressure goes down as height goes up.
Correct. But we still have that variable density, rho, in the equation. We need to relate it back to pressure.
Which is where the ideal gas law comes in. It tells us that at a constant temperature, pressure is directly proportional to density. So the ratio of rho over P is a constant.
If you substitute that relationship into our differential equation, you get something very interesting. You get an equation where the change in pressure, dP, is proportional to the pressure P itself.
And we've seen this before. Anytime the rate of change of something is proportional to the thing itself.
The solution is always an exponential function.
When you solve it, you get the barometric height formula. It is the pressure at any height, h, is the pressure at sea level, P0, times E, to some negative exponent that involves height.
Right. And at first, that exponent looks like a bit of a mess of constants related to the gas law. But if you rearrange it using the definitions of the constants,
The aha moment arrives.
the big one, the exponent simplifies down to one beautiful term, minus mgh, divided by kBT.
Wait a second. MGH?
That's the potential energy
Oh my-
thought of a single air molecule at height h.
Unbelievable. So the barometric formula for the atmosphere is mathematically identical to the Boltzmann distribution. Pressure is proportional to E to the minus potential energy over kBT.
The atmosphere is just one gigantic statistical system. The distribution of molecules across different altitudes is nothing more than their distribution across different gravitational potential energy levels, governed by the thermal energy, kBT.
The same exact law that tells us how many atoms are in the second quantum state of a molecule also tells us how much of our atmosphere is in the first mile above sea level.
That is the power and the beauty of statistical thermodynamics.
That really brings this deep dive full circle. We've worked through some incredibly dense material, but I think we've pulled out three really foundational takeaways.
I agree. First, the Boltzmann distribution, that E to the minus E over kBT, is the universal language for how energy gets shared in any system at equilibrium. High-energy states are always exponentially rare.
Second, we learned that heat capacity is basically just a way of counting a system's available degrees of freedom, F. The simple rule, C mole equals F over 2 times R, is just a powerhouse for predicting the thermal properties of materials.
And third, we saw how quantum mechanics sets the rules for what counts as available. The equipartition theorem fails spectacularly when the quantum energy gap is bigger than the thermal energy. That explains the mystery of diamond and why everything's heat capacity drops to zero as you approach absolute zero.
The journey from an abstract quantum energy step to the pressure of our entire atmosphere, all described by the same exponential law, is just one of the most stunning examples of universality in all of science.
It really is.
Yeah.
And it leaves you with a final provocative thought. We've seen this law of exponential decay govern the distribution of particles across energy levels. Now that you understand this fundamental structure, where else might you find it? Where else in nature, or even in human systems, might the distribution of things, be it wealth or information or population, be governed not by simple linear rules, but by this powerful universal law of exponential decay?
That is a deep thought to chew on. Thank you for joining us on this deep dive into the exponential universe of statistical thermodynamics. We'll see you next time.